It is not a question of whether Europa has an ocean. That debate is finished. The question, the one that keeps planetary scientists awake, is whether something is living in it. Those words belong to Kevin Peter Hand, Deputy Chief Scientist for Solar System Exploration at NASA's Jet Propulsion Laboratory, delivered in 2023. He said them without theater, without hedging. The way a physician states a diagnosis they have already confirmed. Hand is an astrobiologist and ocean scientist who spent more than 2 decades building the scientific case for what is now NASA's most ambitious planetary mission. His research has taken him to the most hostile environments on Earth, to hydrothermal vent fields in the eastern Pacific, to ice-covered lakes beneath the Antarctic plateau, all chosen because they resemble in one meaningful way what exists beneath Europa's frozen shell. Hand's conclusions about Europa are not drawn from enthusiasm. They are drawn from 3 decades of converging measurements, from 4 separate spacecraft, 2 orbital telescopes, and more than 500 peer-reviewed studies, each one narrowing the range of what Europa could be, until only one answer remained. For most of recorded history, Europa was nothing more than a point of light. Galileo Galilei first noted it in January of 1610, a small bright dot tracing a path around Jupiter alongside 3 others. For 3.5 centuries it stayed exactly that. Measurable in its orbit, unknowable in its substance. The first real image arrived in 1979, when Voyager 1 and Voyager 2 swept through the Jovian system within months of each other. What they returned was confusing. Europa's surface was almost perfectly smooth, one of the most featureless objects yet photographed in the solar system. Long, sweeping fractures crisscrossed the ice in arcs of reddish-brown, and there were almost no impact craters anywhere. That absence was the clue. Craters accumulate over billions of years. A world without them has a surface being continuously renewed. Scientists in the 1980s proposed that residual heat from radioactive decay might be keeping the ice warm and ductile enough to erase old damage. The word ocean was used cautiously, if at all. A global body of liquid water seemed extravagant for a moon orbiting more than 670 million kilometers from the sun, where surface temperatures average around minus 160 degrees Celsius. The universe, most assumed, kept its liquid water close to warmth. That assumption was about to be dismantled. The dismantling came not from an image but from a magnetometer. When NASA's Galileo spacecraft completed its first close flyby of Europa in December of 1996, the instrument registered an induced magnetic field, not generated by a rocky core, but created by an electrically conductive layer responding to Jupiter's vast rotating magnetosphere. The only material that matched the conductivity signature and the geometric response was saltwater. Liquid saltwater, global in extent, sealed beneath the ice. Margaret Kyvelson, a space physicist at the University of California, Los Angeles, who led the magnetometer team, described the finding as unambiguous. Scientists almost never use that word. The question was no longer what. It was, what is in it? The ice is the first problem, and it is enormous. In January of 2025, NASA published results from the Juno spacecraft's close flyby of Europa in 2022. Juno's microwave radiometer measured the thermal profile of Europa's ice shell and closed a debate that had divided the field for more than 20 years. The shell averages approximately 29 kilometers in thickness, the equivalent of stacking Mount Everest more than 3 times over in solid frozen water. Some researchers had argued for a shell just a few kilometers deep, making the ocean almost tantalizingly close. Juno ruled that out. The ocean beneath that ice is almost incomprehensible in scale. Current models estimate it extends between 80 and 100 kilometers in depth. The deepest point in Earth's oceans sits at just under 11 kilometers. Europa's ocean could hold somewhere between 2 and 3 times the total volume of all water on Earth, sealed in complete darkness beneath nearly 20 miles of ice on a moon more than 600 million kilometers from the nearest star. The mechanism that keeps it liquid is tidal heating. Europa is locked in a gravitational resonance with 2 neighboring moons, Io and Ganymede, that forces its orbit to remain slightly elliptical. As Europa swings closer to Jupiter and then farther away with each 3.5-day orbit, Jupiter's gravity pulls with different force on different parts of the moon's interior. The result is continuous physical deformation. Europa is being squeezed and stretched, rhythmically, without pause, for 4.5 billion years. The friction generated converts into heat. Think of bending a wire back and forth at one point. The metal warms where it flexes. Now apply that principle to a planetary interior for longer than complex life has existed on Earth. Then there are the plumes. In 2012, a team led by Lawrence Roth at the Southwest Research Institute reported that Hubble's ultraviolet cameras had detected water vapor erupting from Europa's south polar region, rising as high as 200 kilometers above the surface. The detections were inconsistent, and some scientists questioned whether they were real. Then, in 2018, Xianzhe Jia at the University of Michigan led a team that returned to Galileo's archived data from a 1997 flyby. The magnetometer had recorded a sudden shift of more than 200 nanoteslas over just 3 minutes. The plasma wave spectrometer had simultaneously detected a spike in electron density. The only model that fit was a water vapor plume. Galileo had flown directly through active Europa venting, and the evidence had been sitting unrecognized in the archive for more than 20 years. If those plumes are real and active, they represent a direct channel between the ocean and space. The Europa Clipper spacecraft, launched in October of 2024, carries a mass spectrometer capable of detecting individual molecules at extremely low concentrations. It will perform 49 flybys of Europa, beginning in 2030, sweeping as close as 25 kilometers from the surface. If plumes are active at the right moment, Clipper could taste the ocean without ever touching the ice. The chemistry picture has grown more specific still. In 2023, the James Webb Space Telescope identified carbon dioxide concentrated in an area of chaos terrain called Terra Regio. The spectral signature indicated it was not delivered by asteroid impact. It was rising from below. From the ocean. Europa's subsurface water contains dissolved carbon compounds, one of the chemical prerequisites for life as we understand it. Here the honest counter-argument must be addressed. Simulations published in 2024 suggested that Europa's mantle may not be hot enough to sustain active seafloor volcanism. Without hydrothermal vents pumping mineral-rich water into the ocean, the most obvious biological energy source disappears. But there is a second pathway. Serpentinization, a process in which seawater percolating into iron and magnesium rock produces hydrogen gas as a byproduct, requires no volcanic heat at all. Steve Vance at the Jet Propulsion Laboratory found that Europa's likely seafloor composition is well suited to sustained serpentinization, capable of generating hydrogen continuously for billions of years. Life does not need a volcano. It needs a chemical gradient. Europa may have one regardless. If Europa's ocean contains life, even a single microorganism metabolizing hydrogen in the dark, the implications cascade at a velocity that is difficult to think about directly. If life arose independently in Europa's ocean while also arising on Earth, it establishes that the emergence of life is not a singular cosmic accident. It is what chemistry does, given the right conditions and enough time. The number of star systems in the Milky Way, thought to contain ice-covered ocean moons, runs into the hundreds of millions. If life is a chemical consequence rather than a miracle, the galaxy is not mostly empty. It is mostly occupied. The second implication concerns what scientists call the Fermi paradox, the contradiction between the apparent statistical likelihood of extraterrestrial civilizations and the complete absence of any signal from them. One of the more troubling proposed resolutions is the Great Filter. The idea that somewhere between simple chemistry and a technologically capable civilization, there is a step that almost never succeeds. If Europa harbors microbial life, the filter is not between chemistry and the first living cell. Life clears that barrier wherever the conditions exist. The filter is somewhere further along, perhaps between single-celled organisms and multicellular complexity, perhaps between intelligence and a civilization that survives its own technology long enough to become detectable. That resolution is not comforting. It means the silence of the universe may not indicate that life is rare. It may indicate that civilizations like ours do not tend to last. The honest summary of where the science stands is this. The ocean is confirmed. The chemistry is promising. The presence of life is entirely unknown and will remain unknown until we can sample the ocean directly. Clipper will transform our understanding of Europa. It cannot confirm life. For that, a lander would be required. One carrying a drill capable of reaching below the radiation-damaged surface layer in an environment that would degrade most electronics within days. If funded and built, such a mission could not realistically launch before the late 2030s. Brittany Schmidt, a glaciologist and planetary scientist at Cornell University, has argued that the question of life may be the wrong frame for now. Understanding how the ice shell moves, how the ocean circulates, and whether chemical exchange actually occurs. These are the questions Clipper can address. They are the foundation on which the life question eventually rests. There is an old observation in astronomy that the further out we look, the less central we become. Copernicus removed Earth from the center of the solar system. Hubble removed our galaxy from the center of the universe. Each expansion of the map has been, in one sense, a demotion. And yet we are still here, still asking the question, still pointing instruments at the dark. Europa offers something different. Not a demotion, but a possibility. The possibility of a parallel story, another set of organisms, or perhaps just chemistry that has crossed some line we cannot yet precisely define. Running in complete ignorance of ours, inside an ocean that has existed in total darkness since before the first animal appeared on Earth. In 4 years, a spacecraft will arrive at Jupiter carrying the best instruments we have ever built for this purpose. What it hears, or does not hear, will say something. Not just about Europa, about what kind of universe this is, about whether the process that made us is rare enough to be called a miracle, or common enough to be called a rule. We are about to find out which story we are living in,